Welcome to this explainer. We spend so much time obsessing over the sleek aerodynamics of bullet trains, but the real secret to traveling at over 300 kilometers per hour, it actually lies right beneath the wheels. Today, we're dissecting the hidden engineering marvel of high-speed rail, the permanent way.
Let's kick things off by establishing our foundational thesis here. High-speed rail isn't just about fast trains. It's an incredibly complex interlocking system. The infrastructure, the rolling stock, the operating conditions, they all have to work in absolute perfect harmony. Because if even one of those elements fails to meet the standard, the entire system is compromised. Here's our syllabus for today. We'll start with the anatomy of high-speed tracks, move on to rail welding and conicity, dive into sleepers, fastenings, and stiffness, explore how we navigate high-speed turnouts, and finish up with some amazing innovations in crossing design.
Okay, Section 1, Anatomy of High-Speed Tracks, the Invisible Infrastructure. Let's get into it.
So, before we even touch on materials, we have to talk geometry. The 1435 millimeter standard gauge is essentially the universal canvas for high-speed engineering. Now, while conventional tracks in places like India might use a broader gauge, this standard gauge is universally chosen by high-speed pioneers worldwide. Why? Because of its proven utility and seamless interchangeability across global networks. It is literally the foundation of fast travel.
Section 2. Rails, welding and conicity, guiding the bullet.
The absolute most crucial point here. You can't just throw down standard iron and call it a day. For these speeds, you need exceptionally strong 60-kilogram UIC rails, crafted from top-tier 900A grade steel. When you're dealing with the extreme dynamic forces of a train going over 300 kilometers per hour, the quality of that steel must be absolute. We're talking rigorous, microscopic attention to assembly and surface defect monitoring.
But how do you solve the massive vibration problem? Well, engineers use continuous welded rail, or CWR. See, by avoiding standard joint lengths of around 36 meters, they effectively prevent critical, destructive wavelengths. They take standard lengths, like 25 meters in Japan or up to 108 meters in France, and weld them together into one continuous, seamless track. By entirely eliminating those traditional gaps, you dramatically improve the ride quality and practically slash the noise profile of the track. It's a total game changer.
Now, laying the track perfectly flat just isn't going to cut it. To keep the train perfectly centered at those insane speeds, the rails are actually tilted slightly inward. Traditionally, a 1 in 20 inclination is heavily recommended for speeds over 280 kilometers per hour. But networks in countries like Germany have successfully pioneered a flatter 1 in 40 inclination to fine-tune stability for their specific systems. Pretty neat, right?
And that brings us to equivalent conicity. This is a really fascinating concept. Think of it as the theoretical, mathematical relationship between the shape of the wheel and the shape of the rail. As speeds crank up, this interaction profile has to be meticulously monitored and kept as low as possible to maintain stability. If this number creeps up at extreme velocities, the train can actually begin to hunt or wildly oscillate side to side, which, as you can imagine, is incredibly dangerous.
Moving on to Section 3, sleepers, fastenings, and stiffness, absorbing the impact.
Take a look at this Sativa system data. These prestressed twin-block concrete sleepers weigh a massive 186 kilograms apiece, and they need every ounce of that mass for long-term geometric stability. When a bullet train blasts over the track, it unleashes terrifying lateral and vertical forces. It's strictly the sheer physical weight and density of these massive concrete blocks that stop the 1435 millimeter gauge from warping under all that pressure.
But here's the catch. You can't just bolt raw steel directly to concrete. Sitting right between the rail and the sleeper is the unsung hero of the permanent way, the rubber rail pad. Networks like France's SNCF actually swap these out depending on their goals. They might use a normal pad with 90 kilonewtons per millimeter of resistance for standard load distribution, or if they're near a town, they might fine-tune it down to 56 kilonewtons per millimeter with a much softer pad, specifically to deaden the roar of the passing train.
So the ultimate goal here is finding the absolute Goldilocks zone for the whole track assembly. The optimum overall track stiffness is engineered precisely to 78 kilonewtons per millimeter for trains traveling at 300 kilometers per hour. And I mean precisely. This isn't just a random guess. It is a painstakingly calculated variable that ensures the train glides perfectly instead of violently bouncing down the line.
Why does that exact 78 number matter so much?
Well, if the dynamic rigidity is too stiff, the raw physical force of the train simply won't be absorbed by the rubber or the ballast. Instead, all that violent kinetic energy transfers directly downward, and it will literally shatter the concrete sleepers into pieces. If it's too soft, the track deforms, too stiff, and it breaks. It has to be perfect.
All right, Section 4, navigating high-speed turnouts, changing lanes at 300 kilometers per hour.
Just look at this visually incredible layout of a turnout under construction. It really puts into perspective just how long and gradual these track diversions have to be. When you're moving at high speed, making a sharp turn is physically impossible because of the immense lateral acceleration forces. So the switch entry angle has to be exceptionally small, which stretches the entire turnout over a massive distance.
Notice the sheer mechanical density required here. See, the absence of superelevation, or cant, on these turnouts means cant deficiency becomes the single most important safety criteria. Because the track can't bank into the turn like it would on a normal curve, the components themselves have to be ridiculously robust to handle those unmitigated lateral forces.
To combat those intense lateral forces without that helpful banking effect, engineers use something called tangential curved switches. This produces an incredibly flat entry angle. By dropping that angle of attack, the track drastically lowers the lateral forces, which effectively eliminates that awful jolting sensation you get on older, slower trains. It means a passenger can be sipping coffee at 300 kilometers per hour and barely even notice they just changed lanes.
And finally, Section 5, innovations in crossing design, the future of frictionless travel. So, how do we make all this sophisticated tech a bit more environmentally friendly? Companies like Vossloh Kajfer are deploying these amazing lubrication-free systems. They're completely getting rid of the heavy, polluting greases that used to be standard for track switches. They do this by either using quenched steel rollers that let the heavy rail slide mechanically, or through some truly wild surface treatments, where a high nickel and chrome metal powder is blasted onto the sliding surfaces at ultra-high speeds. No grease required.
Check out the heavy mechanical components in this turnout setup. To handle the immense stress localized here, engineers use highly specialized synthetic rail pads and non-greasing base plates, all custom designed to dampen the extreme vibrations of the switch assembly. Every single clip, every pad, every plate is meticulously chosen to keep that track geometry absolutely pristine.
You know that loud clack-clack sound you hear when a train switches tracks? That's the sound of the wheel hitting the impact gap of a conventional crossing. To eliminate that violent gap entirely, engineers came up with the movable manganese monoblock crossing. The internal block literally physically shifts and locks into place, creating a perfectly continuous, welded path for the wheel to roll over.
And the result of all this incredible, seamless manganese hardware, trains are safely permitted to blast straight through these highly complex track sections at a staggering 320 kilometers per hour. And they do it without tearing the switch or themselves apart. It's honestly mind-blowing. We always look up at the sleek aerodynamic trains, but I really hope this explainer leaves you wondering just how much further can we push the hidden engineering of the track beneath them. The permanent way. It's not just static metal and concrete. It's a finely tuned, highly dynamic machine that makes the impossible possible.